3. Rashan needs to go to the other page steps.
Great. Okay. Hello, everyone. Welcome to our first quiz lecture. Yeah, it's a very interesting week. We'll talk about imitation learning after spending a long time on reinforcement learning. And then we'll spend a big part of this course will be combining reinforcement learning and imitation learning. Okay. Okay. So I hope I hope Friday went well. I'm sure it did. And if it didn't go, we have 2 more quizzes. So there's plenty of time for you to do well and study hard and so on. And we also have lots of homeworks. So the last thing to worry is your grade. I think you need to worry about, really try to spend time on the material of this course to really enjoy and use it for your careers later. Okay. So today's lecture is about the basics of imitation learning. So there are limitations in reinforcement learning that we have discussed. And for example, our collaborator Chris Atkinson often says humans very, very little times do they really explore and come up with novel ways of doing things. Okay. Most of the times humans just imitate their parents or their friends or other peers. And the reason they imitate is because trial and error learning requires a lot of interactions. Okay. And it's unsafe. You cannot actually do really unsafe actions in the world. And indeed, kids of little age are all the time into accidents, right? They all the time into accidents. Now, the good thing is that they learn in a very efficient manner, meaning, they do something that hurts them once and they remember, then they're very careful next time, which is not the case yet for reinforcement learning methods. Now, the reinforcement learning methods do improve dramatically from semester to semester or year to year. We have much more sample efficient methods today as opposed to 2 years ago. So, the whole goal of this second and third part of the course is exactly to track the recent progress and what are still the open questions. Okay. Yeah. So we all know the limitations of learning by trial and error, learning by interaction. So that's why we fall back on imitation learning. And there are 2 types of imitation learning. So this is important to always keep this in mind. Each time we talk about imitation learning, we should always be able to figure out if we are in the one or the other category. What humans usually do is visual imitation learning. They watch someone else and they do the same thing. All right. What robots usually do is kinesthetic imitation learning. They have available the actions and they just clone them. They just copy paste actions. What would be the corresponding kinesthetic imitation learning for humans? The corresponding would be you grab the hands of the baby and you just move them in the right way. So you really take over the end effectors of the agent and you show the right action. Sometimes we need to do that, but most of the times we rely that, the human agent can actually copy paste by watching, by observation. Is this clear? The 2 different types? So in visual imitation, the actions of the teacher need to be inferred from visual stream and to be mapped to the action space of the agent. And of course, this is a big computer vision problem. This is the holy grail in behavioral learning and visual understanding. How can I just learn by watching videos? Okay. And of course, as you see, the end effectors of the mom are very different than the end effectors of the little baby. They're much smaller. Many times the baby needs to use 2 hands to actually do the same thing that we can do with 1 hand. And, these things are kind of natural. The baby can actually figure it out. The toddlers can figure it out. And now what has been extremely successful for robots so far is kinesthetic imitation learning. In this way, you bypass the difficult computer vision problem. Otherwise, you need to be stuck till computer vision is perfectly solved to actually give you actions that are, very accurate. So what you do instead is you assume you have the actions available to you. And in fact, there is a killer application right, that many people care about, where these actions are extremely easy to collect. And that application is autonomous driving, okay? It's easy to collect in logs actions that the human driver did and give them available to a robot car and imitate them so that it learns to drive by imitation. Is that clear? Okay. Now, the same situation is a little bit less easy, potentially, for robots. I'll show you some recent, let's say, efforts on large-scale demonstration collection, kinesthetic demonstration collection for grippers, and we'll see why they're successful, why they're not successful, and so on and so forth. Okay. So this lecture is about kinesthetic imitation learning, and we're going to have a whole dedicated lecture on visual imitation learning towards the end of the course. So the notation in this lecture will jump back and forth between what Bellman put down and what Podryagin introduced in USSR. The two notations were developed in the same time. So far in the course, we've been using the Western notation, where actions are A and states are S and rewards are R, and dynamics is probability of the next state, state, and action. And the same thing in the control literature, actions are usually U and states are X and costs are C. So they talk more about costs as opposed to rewards, but the reward is the negative of the cost. Okay. All right. So imitation learning. So we'll introduce imitation learning by contrasting it to a supervised learning task that all of you are familiar with, I expect. Okay. And that task is video labeling of frames. For example, a very hot recent application, which has not so far, panned out, is Amazon Go. Not only Amazon, but many other companies. In fact, I learned also in Portugal, they've invested a lot of money to make supermarkets where humans can go buy products, and there's no cashier, neither person cashier, neither self checkout. It's just their cameras that are watching you, and they know what you picked up and what you didn't pick up and decide to return back to the shelf and so on. So you just grab things and go. Okay. Is that clear? This is the application. So what is the goal? For every frame, we need to be annotating who took what, correct? Which person took which product from the shelf. This is a standard, let's say, action recognition problem in computer vision. And the way we would do it is we'd collect tons and tons of supervised data and train supervised, action detectors of objects that are picked up and their identities. Okay, for example, a detergent, Tide, plus 20 ounces and so on. You need to be really specific on what instance you predict. So you have a very, very long catalog. Typically, you have a huge catalog of all possible products, and it's just a standard classification problem. Okay, so you collect supervised data. Of course, you can do your self-supervised pre-training. We'll discuss about self-supervised pre-training of visual representation simply because they're instrumental in performance in both imitation learning and reinforcement learning from visual sensory input. Correct? Not surprising. And in any case, you train your classifier and you know how to do that. And now the natural thing would be in imitation learning, how this differs, how things become different in imitation learning. The labels, instead of being products, are actions now. Okay? We're labeling frames with actions. In this frame, what I'm supposed to do. Is that clear? Okay. Now, it's a mapping from images to actions. And by the way, the observations will usually use O. Do not think that we pass one image. Okay. So recent architectures take 120 frames and they squeeze them out. They pass them to former architectures. They pass them through recurrent networks. In the next lecture, which we'll discuss, I don't know if we'll have time in the next lecture, half of the next lecture or after your fall break, we'll discuss imitation learning specifically for manipulation. So this lecture is mostly about imitation learning for driving. And then in the next lecture, after we talk about adversarial imitation learning, we'll talk about imitation learning for manipulation and we'll go into more details about architectures and transformers and so on. For now, you can assume we have a long video sequence, okay, and we have a very nice neural architecture that can squeeze information across multiple frames. Then we take that later representation and we map it to actions, and of course, this is trained end-to-end for our supervised objective of mapping, sequence of frames to actions, okay, because these precisely are annotations. Is this clear so far? Okay, so this is our policy, but don't be confused. There are multiple images behind that. Oh, maybe the right thing for me to do is to replicate, in fact, because I don't want you to be confused that it's a single frame to action mapping. Okay, so given that we are so, let's say, familiar with labeling frames, we'll cast imitation learning as frame labeling. But instead of labeling objects, products, we'll be labeling actions. Okay. Now, what is the tiny little difference here that matters a lot? Who would like to say? Maybe you already know, because I've mentioned it before. What is the difference between imitation learning and sequence labeling? This is the sequence labeling is in the bottom. Yes.
Well, with sequence labeling, your next state doesn't depend on the one before. Whereas, it's independent. Well, with imitation learning, if you do an action, the next frame that you see is dependent on that action, and so it's going to have an impact. The action you do now is going to have an impact on the frames for which you need to make an action for in the future.
Yeah. So whether you predicted the correct product or not does not influence what frame is going to come next. While depending on what action you decide to do in the present frame, when you deploy it, your car, and you deploy that action will influence what frame you'll see next. Okay, this is a big difference, and we show this difference visually in this diagram by adding this extra orange connection. So the actions that your policy predicts actually affect your next state xt plus 1. Okay, while the Ys, what you predict as labels of your frames definitely don't affect what the frame is going to come next. The lady is just going to move towards the yogurt, whether you predicted correctly what she picked or not. Okay. Okay. So yeah, other than that, the training data is still sequences of observations, actions, observation labels, observation labels. So in reinforcement learning and imitation learning, our actions influence our future states and the future data, while in sequence labeling, our labels definitely do not influence the future frames. Okay. Is that clear? Now let's see what implications this dissimilarity has. Well, it has, as a result, the fact that there is a distribution shift between training and test time. And here I'm going to visually show you what I mean. Imagine that we want to learn to drive using kinesthetic imitation learning, something extremely reasonable. In fact, today's lecture has 3 papers that all learn to drive with kinesthetic imitation learning. Okay, one is too old, 1980s, so you don't have it as required reading, but we'll cover it in our slides. So in that application, the training data are expert trajectories, whatever you see as the blue dotted curve on the slide. All right. So our goal is at every time step to predict the steering angle of the expert. Now, test time, let's say we managed to do this training. We took all the observations of our expert and predicted the correct expert action. Now, at test time, we'll deploy our policy, okay? And once we deploy our policy, we're in a particular state. We wake up in a state where it's very similar to the state of the expert. Now, we deploy our action, and our action naturally will have a tiny bit of error because this is it's a standard machine learning algorithm. You have a bounded error. Now, the problem is because of that tiny little error, your resulting observation will be tiny bit different than the observation that the expert saw. All right? But interestingly enough, you are not trained on that deviated observations. You were never trained on deviated observations, so you don't know how to recover. All right? So you'll see now this a little bit, novel observation where you actually see much more shoulder, the shoulder of the road, much more shoulder or off-road scenery that you're used at training time, and you'll make a prediction with your policy that again will have error and potentially even larger error. And that worst action will push you even further outside of the road. And then you'll see some even more, let's say, unfamiliar observation, and then your policy will go crazy, okay? So the reason is that you did not learn how to recover because you were only trained from all clean expert trajectories. This is the problem. Very simple problem, very intuitive. So what does this mean? This means that the distribution of observations of the expert pi star, the expert policy that supplied our training data, is different than the distribution of observations that the trained policy pi theta sees at test time. All right? And because it's different, we have zero guarantees about the errors of the policy. Okay? So in supervised learning, both x and y's are sampled from the same distribution D. But when there's supervised learning and control, which is imitation learning, we have this distribution shift. Is that clear? Okay. So basically, the problem is the following. Imagine that the nice green curve is an expert trajectory. Okay, very beautiful, very clean. And imagine that each time step, you wake up at a state on that green trajectory and you execute an action. And so you execute your action, you deviate a little bit. But in the next time step, you don't wake up in the observation or on the state that will result if you apply that action. Rather, you again sample the next state along that expert trajectory. So you never deviate. You always have a small bounded error around that expert trajectory. All right? Because this is just, you test yourself exactly how you trained it on sampling observations from the expert. All right? Now, once you start deploying your action, then deviation starts. All right? You start from a state that's the same as the expert, you infer your action, you deploy it, and now you land in a state outside that beautiful trajectory, and again, you deployed your action, and so on and so forth, and we don't have, basically, we cannot bound the error linearly anymore at every time step, and that is precisely the problem of distribution shift. Okay. So now the question is, how can we recover? How can we recover? By the way, do you remember when we have seen that problem before? We have seen this problem in the course before. We have seen imitation learning before in the course. Does anybody remember? Yes?
Was it when we were trying to use planning with the Monte Carlo, but we were trying to do that with like the policy gradients? Not the policy gradients. Was it more trying next Q learning?
Yeah, exactly. So your colleague's saying, we've tried this before. The experts in that case were not humans, were planners, and that's totally fine because planner is still something more intelligent that can use time wisely to come up with good actions. And we were imitating the planner. And if you remember, we said that if you don't do interleaving between querying the planner and learning your policy, then your policy will not be competent because as it plays Atari is going to land on images that your expert planner has not told you how to play. You remember? And then the way we recovered was with interleaving. All right. So this will be one of the three solutions that we will see today. Interleaving, iteratively querying the expert. Okay. Now there is an easier first solution, which is called data augmentations. We'll just be augmenting our trajectories. Let me show you how. So instead of only training on the distribution of observations from the expert, we'll actually augment those expert demonstrations. And how we'll do that? I'll show you in three different ways. So why we'll be augmenting? So that we'll be making that distribution of the expert wider. So it can cover the observations that I will see at test time during deployment. How we'll do that? Well, either we'll do this augmentation through generating synthetic observations and labels. Either we will use clever hardware, and this clever hardware will allow you to use true observations, true images, but with synthetic labels. When we do augmentations, we have two things we need to worry about: the observations, the images, and the labels, the steering commands, okay? Both of them need to be generated. so that you can use them as additional training data to train on. So, and the last way we'll do that is by interactively querying the experts in additional data points. And this is precisely the third category, is the interleaving we saw with our Monte Carlo tree search planner as expert. Okay. All right, and we'll see what are the pros and cons of the different ways of doing these augmentations. So let's go to the first, by generating synthetic data in simulation. So we are actually very proud because in 1992, okay, here in CMU, Pomerleau built that vehicle. Now I want to show it to you. Here is the vehicle.
By watching a person drive. Alvin is designed to control the NavLab too.
Yeah, just a second. So it is a vehicle that drives on its own, trained by a human expert, as well as in simulation, both ways. It has a very tiny 3-layer neural network, extremely small, okay, because there was no hardware back then. And it is trained only from 1,200 training data in simulation. Now, let me tell you, this, of course, was not enough. 40 epochs, you pass them 40 times, and that's it. This is train the network. And you see the simulated data looks like this. Or maybe, yes, so some of them are simulated, some of them are real. What happens is you pre-train in simulation, and then the human driver drives in the new park where you landed, and you use that data of that human to fine-tune your network, okay? Because the network has so tiny capacity that you cannot learn on some different texture and generalize on different textures, okay? Now, once you drive a little bit and, we fine-tune the network, then, you can leave your hands and you'll see that the vehicle is going to go. Of course, there are no other traffic, no pedestrians, nothing. It's just road following. That's all it does. It just follows the lane, okay? All right. Now, I'll tell you why this is interesting, but let's hear first what's going on.
Alvin is a system of artificial neural network. While Alvin watches.
So here you're teaching it.
Seconds, Alvin digitizes a video image of the road ahead and records the person's steering direction.
Yes, it records the steering direction, okay? It collects training data while you're driving the vehicle.
This training image is reduced in resolution to 30 by 32 pixels.
So here it becomes very small.
Input to Alvin's 3-layer network.
This is, by the way, fully connected, right? There's no CNN there.
Learning algorithm. Alvin is trained to output the same steering direction as the human driver for that image. Initially, the network steering response is random.
I mean, sure, it's randomly initialized.
After about 2 minutes of training, the network learns to accurately imitate the steering reactions of the human driver.
Okay, 2 minutes training.
This same training procedure is repeated for other road types. After the networks have been trained, the operator pushes the run switch and Alvin begins driving.
Alvin begins driving. By the way,
per second, Alvin digitizes an image and feeds it to its neural networks.
Yeah, to predict the steering direction.
Each network, running in parallel, produces a steering direction and a measure of its confidence in its response. The steering direction from the most confident network.
They even had ensembles.
The network trained for the one-lane road is used to control the vehicle.
Okay.
Suddenly, an intersection appears ahead of the vehicle. As the vehicle approaches the intersection, the confidence of the one-lane network decreases. As it crosses the intersection and the two-lane road ahead comes into view, the confidence of the two-lane network rises.
Okay. Great. This is good. So they even had 1 lane, 2 lane. Okay. So is this single lane or is it 2 lane in front of me? And you train with the data, and basically they also spit out the confidence, and you trust one member of the ensemble or the other, depending. So basically it's like a mixture of experts here driving. Yes. Yeah, the speed is not predicted. Yeah, only the direction is predicted from the net. Right, so they put a slow enough speed so that, things happen online. Otherwise, it cannot drive, right? Yeah, it is pretty amazing. And here is the most amazing thing, that the problem of distribution shift had already been, documented by Pomerleau in 1989, saying that the network must not solely be shown examples of accurate driving, but also how to recover, okay? How to return to the center of the lane once a mistake has been made. And because a human doesn't give you this type of training data, I need to use my simulator, all right? So basically they simulate observations by, instead of, taking a picture of the lane, here's your lane and you have your environment, you shift the camera and you take a picture and you synthetically add a label that tells you go back, okay? Because you know how much you turned, you know how to add your synthetic label, if that makes sense. So you do need to do that, otherwise it doesn't work. Okay, so this is exactly the same problem that we've been discussing. And graphics back then were extremely slower, and it was slower to render the images than training the network. It took a long time for the for the simulator to work. Now, how can we scale that to real driving? Okay, this happened a long time ago. Now, we'll visit one very intelligent paper, I think, which, you don't need to rely to a simulator to generate these off-road images for you, because simulators naturally will generate images that are not photorealistic. Rather, you will just add 2 cameras. You'll have your center camera and you have side cameras left and right to tell you how would the image look like if you would make a mistake. And then synthetically, you would add the label to tell you, if this is what you see, then go back to the left. If this is what you see, go back to the right. Now, let me show you how this looks like. Okay, so this is end-to-end learning for self-driving cars from NVIDIA in 2016. So here is the car, and it has 3 cameras, the center and the side cameras. And the side cameras are not used for driving. Okay, they are not used to feed input into the policy to ask for actions. They used only to generate training data. And this all the time we ask in the quiz. The left and right cameras are used to generate synthetic training data. Well, it's not synthetic because the images are real, but the labels are synthetic, meaning no human expert drove facing the shoulder or facing the grass. We synthetically generate this to you so that if your train policy makes a mistake, you will know how to recover. Is this clear? Do you see what I mean? Is that clear? So the left and right cameras basically they shift off the center of the lane, and you can use this additional training data along with an image and ground truth action. You have now 2 more images and actions of corresponding recovery modes, one from left to center, the other from the right to center. Is that clear? Do you see how intelligent this is? Simply by adding 2 extra cameras. And let's see. And this is the system is called Dave 2. And actually here they say that it was inspired by the pioneering work of Pomerleau called ALVIN, which stands for Autonomous Land Vehicle and Neural Network. Okay. And training with data from only the human driver is not sufficient. The network needs to recover from mistakes. So now, here is the updated pipeline. Okay. So in any case, it is not that impressive now. I'm sure you've seen tons of video of autonomous vehicles, but basically we don't need now anymore to online adapt. We can generalize across environments. The neural network is not 3 layers, it's very deep, has convolutions and so on and so forth. Tons of training data collected from very diverse conditions. As I said, self-driving companies have tons and tons and tons of such driving logs, okay, to actually train these architectures, to drive with imitation learning. Is that clear? Okay, and here is another application of imitation learning. We're going to train a drone to follow paths in the forest. And again, we'll have our expert. So this is our trail runner. You see him here, okay? And he wears in his head those 3 cameras, all right? Very much same intelligent trick as what Dave 2 did from NVIDIA, all right? Where the left and right camera just push you towards the center of the trail. That's all. So you let the human driver run. Naturally, it collects the training data because you have IMU sensors and you know the direction where he's going, okay? Or maybe also you use visual odometry to estimate the pose. That's all you need to know, the steering angle, okay, of how your drone should be moving. And you can do a great job. And now to you, it may look obvious. It may look obvious to do that, to teach a drone how to drive, how to fly. But I want to mention that there was a project here in CMU where actually they tried to use the 3rd bullet. Instead of using intelligent hardware, they tried to use Dagger dataset augmentation by querying human experts to fly drones. And it was not successful. It was not successful because for the reasons that I'm going to discuss right now. So the last solution of augmenting your data is just go back to your experts and ask for more labels. And if your experts are planners, this is very easy. In fact, we did it already. But if the experts are humans, things are getting very, very difficult. First of all, humans never drive and they see next to them the tree and they're about to crash. This stresses them out. They overcorrect. Do you see? It's very difficult for a human driver to accurately tell you how to recover from a mistake. Is that clear? And indeed, when you ask them, you show them how the drone was actually flying towards the tree and you ask them to correct the trajectory, the humans actually would what? Overcorrect, and then you would give them a visual interface to actually see their corrections and so on. It was very, very difficult, let alone that many drones were killed, right? Because they would, because then you deploy an unsafe policy. That's the problem with Dagger. That's I'm going to show you right now. You have your expert trajectories, you collect your data, you train a policy, then you deploy the policy does pretty badly, then you go back to your experts, you query for more data and so on. And this has the problem of deploying an unsafe policy in the environment. And that's precisely why the drones would actually crash, okay? Very natural solution. I don't see anything difficult here, guys. Basically, here is the procedure. We take the ground truth human data, train a policy, deploy the policy, collect new data, ask the humans, aggregate the data set, retrain, and so on. And the problems is whatever we said, that first of all, you need to deploy an unsafe and partially trained policy in the environment. And it's very difficult to get accurate labels from humans in dangerous situations. All right. So that's why we do Dagger when our experts are usually not humans, for example, planners. And it makes a lot of sense to imitate planners. And we'll see many applications where you have planners solving the problem from different conditions, okay? We're simplifying assumptions and then distilling and imitate them into big neural network policies. And the good thing about the neural network is that now this can generalize across all the conditions, while every planner works on the very specific initialization and so on, okay? Initial state. All right, so here is the drone that I told you that is the problem. This is the 2013 paper. And the problem is that it's hard to an expert to provide the right magnitude for the turn and so on and so forth. So this is very important to remember. Experts do not need to be humans. One algorithm can be teaching the other algorithm to behave and to act, because one algorithm may be more intelligent in a particular setup than the other. All right. And MCTS was one reason for that. MCTS was intelligent, but very slow. The neural network was fast, but it couldn't search well. So it makes sense to train the neural network by imitating much slower MCTS planner. Okay. Okay, so we will see a very successful such paradigm where we're going to be using ILQR, trajectory optimization, to give us solutions for, let's say, manipulation problems, and we'll be distilling the solutions of those problems into neural network policies. And this is a very famous paper from 2017, end-to-end learning of visual motor policies. That was the first paper where a behavior policy was actually trained with a neural network. Nobody would imagine to do that before, because they didn't know how to collect that much data to train a network to manipulate objects. But, they did it in this way of, imitating planners, basically, as opposed to, DQN and so on, which is super sample inefficient still. Okay. Any questions so far? Nothing. Things are straightforward, I think. So let's see then a nice paper here that applies imitation learning for driving. Now, driving is, a domain that of a big industrial interest. There are many academics also working in this problem. For that reason, people work in simulation. There are famous simulators. One of them is Carla that people use. There are benchmarks there. Different scenarios that you need to beat them. You have an algorithm. You are scored on different scenarios of the benchmark, and there is a ranking of which one performs the best, and so on and so forth. And right now, the most, let's say, highest performing methods are from imitation learning. Okay, and this is very natural. And here is a paper that has a very nice trick, and that's why I want to present this to you. So they call it learning by cheating. So they say, I have some, for example, human trajectories, all right? Instead of directly training an agent that can drive from image pixels, I will first train an agent to drive from that, semantic map representation. There's an overhead map. What you see here is an overhead map where the lanes are indicated in the map. As you see, the cars are blue, stop signs are red, the purple dots are the past trajectory of the car, green is the lights, potentially green light, and so on. You will train first an agent with imitation learning to drive, to predict actions, but not from image pixels, but from such privileged visual input where perception has been solved. Is that clear? And then, once you train that agent, you will imitate that agent. So you will then deploy that agent, and then you will train a sensory motor agent whose input is perspective images, just what the camera is seeing in front. And the question is, why is this a good idea? Why would you not take your human expert trajectories and directly train with imitation learning the second agent from images to actions? This is the question. It's not a very easy question. So Maxwell wants to reply. Does anybody else want to reply? Okay.
You might use higher level representations that you can later map low level to when you use the actual sort of photorealistic data.
Okay, this is not very, for example, now that you told me, I'm not sure I get it. It doesn't sound intuitive. I have some training data of, with trajectories in the simulator. So these trajectories are from the simulator, right? And I want to learn to drive from image pixels because that's what I will use at test time, let's say. Okay. Why can I not just do whatever we just discussed directly from the expert data, training a policy to map images, the images from those expert trajectories? Now, just to be clear, these expert trajectories have available both at overhead map because you're in the simulator, right? In the simulator, just to understand for those that don't know what's a simulator, it's as if you're God. You know where all objects are, everywhere, the pose, everything. So you have access to that representation, the privileged representation of the world. But of course, you also have access to the renders because that Oracle representation is rendered and gives you images. So the question is, how can I use these expert trajectories? And these people had this decision. Yes.
So you have more information in the privileged view than you do in the photorealistic one. And maybe the agent can learn some sort of internal model of dynamics and predict what's like not there to help itself.
Okay.
Can just partially observe with the photorealistic.
Right, but just remember, guys, that at the end of the day, this the way that I'm going to distill information from the privileged into this other guy, I'm just going to render more trajectories. So the question is, why the trajectories of the privileged agent are better than the initial human expert trajectories? Do you want to say something?
Because we don't have those challenges that we have when we have human experts trying to deal with improper driving. If we get a reliable privilege agent that's easier to solve, once we get them to let that train on its own, then we can use those expert demonstrations that don't have the issues that are inherent. Right.
Okay, but what are those problems that are so basically, just to be clear, like just let me focus the discussion again. So the question is the following: why is it better to learn from trajectories of the privileged agent as opposed to directly learn from trajectories of the human experts? That's the question, right?
You can make changes in real time. You can query it, right? You do that for sure. And how would I fix that with the privileged agent? But rather than providing
I see. So your colleague saying is the following: if we train that privileged agent, okay, well, you don't fully said it yet, but you're getting there. Does anybody want to add something? Do you want to add something or no?
Well, I guess it was just a similar idea that you could generate a lot more trajectories.
Oh, great. So you want to generate a lot more. How are you going to generate those trajectories, for example?
Just use, you could essentially do like the model based on
Yeah, okay, this doesn't sound super, I mean, this Monte Carlo that you just said doesn't sound super straightforward, right? Because Monte Carlo requires that you know how the environment behaves, right?
what the privilege agent has. It just has sort of, it doesn't have dynamics.
Yeah, the privilege agent just has mapping of the privileged state of the world with action. Yes?
The privilege mode also follow the policy that your agent is following.
No, they may not follow the policy that.
We could generate worse, like trajectories where you have those, issues where like it's heading towards a tree, and you can like correct that. Whereas it's a human agent, the sensor input you can't necessarily.
Okay. So guys, let me tell you, I think what you're alluding towards is that somehow we're going to learn the dynamics of that world model in that awesome Oracle state, and then we'll be able to use that model and generate more data, which sounds pretty open problem to me itself. Okay. While the solution sounds actually terribly easy. Yes.
We have the privileged agent, and we can run it as many times as we want.
We can, yes.
And we can change around other things in its runs, and then render all of them. And then that's a cheap way to make a lot of data.
Right, I agree. So now your colleague says, "Oh, look, we'll run it a lot. Hopefully, it's going to work, and maybe we can add more data and fill in the gaps of the human expert data. Let's say, yes."
You could honestly just control the steering on your own and drag around the agent so that you can collect those trajectories. Right? So you can effectively use that data itself.
Yeah. Okay, so here is actually, you are very close. You are all extremely close, okay? So the idea is the following. We've talked about augmentations. It's all about augmentations. It's very difficult to augment the pixels. But it's easy to augment your past trajectories. So essentially, you as a human, can go and manipulate that state and say, look, let me show you how to manipulate the state. Yeah, so privileged agent cheats. It privileged for the car to follow, and sensory motor. Okay, yeah. Yes. So here is what you can do. You can do random rotations of, if the agent This way, make sure that you correct it. So you can create synthetic data in that oracle state, you see? But you cannot create synthetic data in pixel space. Do you see? Because you are not, you don't know how the world looks like. While in that state, you can say, you know what? If your dots are approaching the shoulder, make sure you push back. So you can create this extra synthetic data on your own as an engineer, using that engineered map. And that is precisely the data that you need that the expert human trajectories do not have, like correction data. Now you may say, okay, this is not super impressive. It doesn't really cover crazy scenarios and so on. I totally agree. But this has shown to be extremely important to handle the distribution shift. This is precisely our discussion so far, that we need to do augmentations. It's hard to do augmentations with pixels. I mean, you may say, look, I'm going to add the left and right cameras and do the trick that the NVIDIA people do in Carla. Oh, well, sure. That's one thing. The other is to go through that privileged agent. So I like that paper exactly to show you the importance of augmentations. There is another paper that was also very good, actually called ChauffeurNet, again from Waymo, I think, Google, again with similar synthetic augmentations. And right now, there are all the state-of-the-art paper drive from that oracle state of the world, and they do all these crazy augmentations of, oh, my trajectory may go to the right and so on. And you create those synthetic augmentations too as the engineer. Much like the computer vision engineers take an image and they crop it and they rotate it and they warp it and they say, oh, this is still a chair. The same way you warp the trajectory and deform it and say, okay, this is your next state. You better push back in the center of the lane. Is that clear? Yes.
Not sure I'm understanding why you would need to go through to look at this privileged world. Why can't you just use that map to then render as many sort of 2D pixel images as you want?
But you also need the corresponding action decisions, right? So you want to pair the map with actionable with trajectories, right? We care about road following and the fact that now you need to stop on the red light and that here you need to slow down here not to crash the person in front of you. And what you're saying maybe is like, look, I can even train a planner but you know what is not that obvious? It's not that obvious to learn how to weight all these parameters. Okay. In fact, the whole point that we learn by imitation is precisely we don't know how to code up a reward function where nice behavior, driving behavior is going to be generated. The humans will be okay to stop in the middle of the intersection. Once you see, let's say, an old lady, you really know you should not go through the human. But you need to balance the reward of, oh, I violated the green light. Like, look, I'm stopping in the middle of intersection versus, oh, I'm avoiding an accident versus, oh, don't put those humans in danger and so on. So balancing those rewards is unclear. So imitating trajectories of humans allow you to do this automatically. It teaches you how to drive in this situation. So the only thing you gain going through this oracle agent is just to augment those trajectories. That's all. It allows you to do augmentations in that synthetic space. Yes?
Is it possible that the model will also learn to make the mistake that was made in the first place?
Which mistake?
Like they're introducing some mistakes in the trajectories and fixing them, right?
Yeah, we don't introduce it. So we just give it extra synthetic data ourselves, okay, by taking the actual training data of the human with some deviations. The only thing this teaches that the privileged agent is how to recover. Exactly what Pomerleau did in his own vehicle. So now we have learned an agent that can recover and thus can drive effectively and can teach the, sensory motor agent. And now the sensory motor agent that drives from pixels can query all different ways of, oh, what if I see this image? Oh, what if I see this image? So now our privileged engine can answer basically because we trained it to handle those crazy situations. Do you see? Yes?
Question about the simulators. So does Carla have like a fixed rule with like defined trajectories for like other vehicles and pedestrians, or does it like randomly generate like that section of the world?
It spawns and randomly spawns on cars and so on. And the simulator is being updated. Before it didn't used to have pedestrians. I think the latest versions also have pedestrians and so on.
So when we're training the privileged agent, we're still like randomly generating the world, but we just look at a section around it, like from like a top level view?
Right. We look at the top level view and we look at the semantics of that top level. Like you don't see grass anywhere, right? It's irrelevant. You just decide which labels to keep, which is the lanes, the cars, and the traffic lights, and the stop signs, and so on. And this is only what you keep in your map, right?
So even in this like world view, the other vehicles and pedestrians are like still moving around.
Yeah, they're moving around. Yeah, like what you see as other blue is the other cars. Okay. All right. I thought that's kind of interesting. So let's see. Why learning from a simplified input? It is the same supervised learn problem. And the thing is, yeah. So the map representation affords simple and effective data augmentation via rotation and shifting. That's all. That's the only benefit of going through that privileged representation. Okay. So basically, we're able to do Dagger, right, by first training this agent that operates on semantic maps and doing ourselves the augmentations for it. And later, as a sorimotor agent, can query for arbitrary, correction of or road following and so on. Okay. All right. Another thing that potentially you want to remember here is the following. The policy predicts waypoints where I should go on the road, and there's a low-level controller that follows those waypoints. And we'll see why this is a good idea in our Sim to Real lecture. We'll show that while the dynamics of every car are very different, and that what is exactly the forces and so on that you need to apply to follow a particular waypoint varies from cars. What waypoints to follow are the same across cars, right? So the waypoints interact with the external world and are the same across cars and make sense to imitate them. And they also jump very well the Sim to Real gap, while the low-level control doesn't, okay? Because the dynamics of every car is different. Okay, that's it. So the next topic for today's lecture is something extremely simple and intuitive, which is about imitation learning for diverse goals. So far, all our policies had a specific goal in mind, okay? So all our policies were mappings from state to actions. So now in this last section, we'll show policies that are mappings of states and goals to action. This is very important. In this way, you'll be able to train one policy across multiple related goals and share information and examples across each, okay? For example, we want to be pushing objects to diverse different locations. You need to be able to communicate to your policy where you want to push the object. And by the way, for driving, I want to tell you that input is also a goal location of the agent which is somewhere far away, like 40 meters ahead of it, that tells you which direction the car should go. Imagine you have an intersection, you need to indicate to the policy that I don't care about turning right, I actually care about going forward. And you can indicate this with some 3D, location on that overhead map or some, distance ahead of you from the vehicle, okay? All right, so we'll go back to an architecture that uses transformers potentially in 2 lectures from now, where we'll actually discuss first those architectures in more detail. So exactly, so we want to be pushing objects to diverse locations, pouring to different bottles, driving to different goal destinations, so on. So naturally, we need to condition our policy to these goals, of course. And how can we do that? Well, both the value functions and the policies, instead of being a mapping of state to values or state to actions, is going to be a mapping of states and goals to values and states and goals to actions. That's all. That's the only difference. This idea was introduced first in Universal Value Function Approximation paper of Scholl et al., but it's extremely natural. The only thing is going to change is that our experience tuples, and by the way, right now we're jumping back to reinforcement learning, because both reinforcement learning and imitation learning, we will need to handle multiple goals, okay? So instead of our tuples being state, action, reward, next state, our tuples become state, goal, action, reward, next state. And I should be able to learn a policy that handles diverse goals. Okay. So basically, guys, what I'm trying to do is the following. I want to present a paper to you. It's called Goal Condition Imitation Learning, where there's also a goal communicated demonstration. It's just extremely natural. The ideas of multiple goals first showed up in reinforcement learning. And now I'm going to show you a very, very good paper of 2017, with a very interesting augmentation method, data augmentation method, which is called goal relabeling. So now you're going to see what benefits you get when you learn multiple tasks jointly with one policy. All right, what augmentation opportunities you get. All right. So basically, the goal conditioned behavioral cloning, just to be clear, it's extremely simple. Every trajectory will have an extra annotation, which is the same for the whole trajectory of what is the goal, whatever you see in red. And the policy network will take that goal description as input. All right. And with transformers nowadays, as we're going to see, it's extremely simple. The goal is just an extra token. You attend to it, and it's extremely natural way of conditioning. Okay. Now, what is goal relabeling? Here is the simple idea of goal relabeling. Imagine that you have a particular goal, and you have a gripper, and your goal is to actually put your fingers around that particular red spot. All right. Then you're like, oh, I really want to put my gripper right there. Then you say, okay, let me start. Let me apply some random actions or random weights. I initialize my policy randomly, and look, I landed some really far away. And then you're like, okay, I didn't get any reward. I was not able to reach that location. But guess what? Your failure under the original location is actually a success for an alternative goal. All right? And while you didn't get the reward from the initial configuration, you actually got the reward for the second one. And actually, this is extremely important, this switch from 0 to 1. All right? Because, of course, your failure under the first goal is actually failure for many other goals. But what we care in reinforcement learning, where rewards are so sparse, is to switch that reward part of the tuple to 1. And under this alternative goal representation G prime, then indeed you get reward 1. All right? So this is similar to, I try to write a paper, I have a particular goal in mind. Well, I fail to show that, but something else came out. You're like, okay, I'll write a paper for that other thing that actually I achieved. Okay? So we use failed executions under one goal as successful execution under alternative goal G prime, which is precisely where we ended at the end of the episode. And my question for you is, when do you think this is going to work? Yes, what is your question?
I don't know how they will generate data for this. What's the situation in which people figure out, okay, this is successful for this other goal? Do humans have to do that?
A great question. So let me give you a specific configuration. Imagine that you have a gripper and you want to learn a policy to reach to different locations of your 3D workspace. Okay? And you are in a simulator, so you know exactly where you reached. And you're like, okay, my goal now is to reach this location. All right? And then you start your policy randomly, and you do your actions, and your actions are probably, delta of orientation and, translation of your gripper, and you land here instead of landing there. Then you're like, okay, I reached this location on my workspace, and let me add this positive tuple there. Okay? All right. So the motivation behind this, so here's the paper, Hindsight Experience Replay, is our reinforcement learning has been criticized of being very, let's say, sparsely supervised. Indeed, if you have a goal in mind and your goal is to pass the Montezuma's revenge level 1, you'll spend all your life getting 0 reward. And when you get 0 reward in reinforcement learning, nothing changes. You don't learn anything. This is all wasted experience. Okay? And that's why learning models comes in that says, it's not important to follow specific goals. It's important to learn how the world works. Okay? It's important to learn, for example, that you are actually able to go up that staircase. Okay? You didn't manage to get the key and put on the door and so on, but look, you can go up that staircase while you cannot go up the wall, for example. And this is actually need to be, saved. So in that paper, basically they say with goal relabeling is as if, the supervision is not like the single cherry on the cake. That's what LeCun says, that reinforcement learning is just a cherry, and there's a cake below that needs to be self-supervised. And now here, reinforcement learning people say, look, you can put more cherries by having goal relabeling. Okay. Now the truth is that goal relabeling works well for some problems and not well for other problems. It works well when you fail is actually useful. Now for reaching, it's very useful because no matter what you do, somewhere you're going to reach. But if your goal is to open this box in front of you, many failed executions will actually not give you anything. Well, I mean, if you already know how to reach places and you've already learned the reaching and you master the task, more failures here will not actually be useful for the task of opening or for the task of grasping and so on. So when the goal is actually a thin tunnel, okay, where you really need to get some sequence of states correctly and all surrounding is failure, such goal relabeling doesn't actually help much, if that makes sense, okay? Okay, but in the time that this paper came out from OpenAI, reinforcement learning methods could not even learn to reach effectively, and you can imagine how massive acceleration such a goal relabeling can give in this type of setups. For example, one is reach everywhere. The other could be push the object in different places of the workspace. Maybe you push it and it didn't go in the location you wanted, but it went somewhere else. Now, if you didn't actually manage to make contact, then you're just fail, okay? Then you cannot just boost success of an alternative pushing goal because you didn't actually make even contact with the object. I think it would be useful for you to know this idea. So now, what can you do with goal relabeling? You can get your favorite reinforcement learning method and not goal relabeling. That's all, okay? And instead of training to push the object a particular location of the workspace or reach a particular location, you can create a family of goals of reaching in general to somewhere or of pushing the object somewhere and change your pseudocode so that this goal relabeling is, accommodated. And here is one way to do it, okay? What we need is enough policy reinforcement learning methods, for example, DQN or DDPG that we have seen, all right? And policy to sample goals. And here where in Oracle environments and the goals could be X, Y locations on the table in front of us or X, Y, Z in the workspace, okay? And so on. So what do? We always sample goal, which we didn't have before, if you remember. So you always need to start by sampling goal G, and then you fit it in your policy and your policy. Now you have trajectories, and these trajectories have reward, yes or no. And for the trajectories that actually are failures, you will go and, so this reward function is precisely the reward, how close to your goal. It's very important when you create the trajectories. And here is the relabeling part. So sample a goal, we said this is important. You need to store the transition, the tuple, the same as before by appending the goal, okay? And the policy is conditional. And here is precisely relabel part, okay? So you grab a G prime, which oftentimes will be the last state in your trajectory or some intermediate state of your trajectory. And then you'll say, now the reward under that alternative trajectory hopefully will be 1. Of course, you can do tons of relabeling with 0 rewards, but it's not going to be very helpful for you. The most useful augmentations is those that are failed tuples under 1G are actually successful tuples, reward equals 1 under this alternative goal representation. And that's it. You just throw those in your replay buffer, and that's you have nothing else to change. We had a homework exactly on hindsight experience replay with DDPG up till 2 years ago. But now, it's a bit less in fashion, so we just remove that. So whatever you see here as, let's see. Right, so if you see no hindsight experience replay is the dotted red line, and you see that for very long time, there is actually no reward. In the y-axis, you see the average success rate, and without this goal relabeling, the reinforcement learning cannot actually kick off the ground. Does this make sense? Okay, it's actually very, very important. Now, the different curves that you see are different methodologies of doing goal relabeling. Shall I grab a state at random? What they call a random is, shall I grab a random state to do goal relabeling? Shall I grab the final state, which is the blue? Shall I grab any future state as opposed to only the final one? So different ways of doing goal relabeling generate all these different curves. All right? Yes, please.
Can we, I'm just curious, how would we start to apply this to Mujoko, or we can't apply this to Atari?
Yes, we don't. Let me think. We cannot apply this for Atari. Well, I think a very good question you're asking is, what is your goal representation? So we'll visit the paper. So this goal representation is XYZ locations. There are no pixels here. Both the state, the input to the policy, and the goal representation is just XYZ of objects, which is extremely engineered. It assumes that you have perfect computer vision. Now, if you want to do the same thing from pixels, there is a paper. It's called Reinforcement Learning with Imagined Goals. And we can visit it simply because, some papers, don't really work, but are really, really very helpful to teach us, to connect dots and so on. So that paper, basically what it does is you have a gripper and you deploy your policy, and you collect images, and you learn a variation autoencoder of your images, which is a generative model. All right, which means what? You learn a network that if you sample random noise and you feed random noise, you'll get an image at the end. So every such image is, let's say, a goal you may want to achieve. Do you see what I mean? So you have now visual representation of your goals as opposed to being XYZ. So yeah, so now you sample from that goals. That's exactly how you sample goals, because the most important thing here, guys, which is, I agree. I think the most important questions are, in lines. How do you even sample a goal? This requires visual common sense. How do you know what's a reasonable goal to achieve in the environment, right? If I knew that, then I pretty much know how the world works. Well, here, essentially, you put a very clean, representation of the problem. You're like, my goal is to learn to reach, and the goals is such and such, and go ahead and do it. And this is not a general formulation that you can apply, okay? But yes, basically there are extensions of this methodology where they create generative models of the pixel space, which they use as goals. So we will visit those later in the course. Does this answer a little bit your question?
Yeah.
It does. Okay. So I'll note down to make sure that we take this paper later. But by the way, I want to tell you some papers are way more, let's say, applied, and some papers are less applied. For example, the Dave 2, actually it was on a real vehicle, okay? So that was an imitation learning method that really works from images with large-scale data deployed on a real robot vehicle platform and so on. Some are a little bit more on the research side and, try to introduce some ideas, etc. Now, the next 1.5 from today, or maybe the next 0.7 lecture ahead of us, we will see imitation learning for manipulation that actually works really well. I'll show you some real robots. They will do very nice diverse tasks and so on. So just wait. It's not going to be that single gripper doing, random things on extremely constrained Mujoko environments. Okay? Yeah. But this is reinforcement learning. And this is what I'm going to describe will be imitation learning. Okay. So the only thing I wanted, so here is pushing, sliding, and pick and place. These are the tasks, okay? And there is also a very sneaky sentence in the paper in the experimental section that says, for grasping, we actually had to add the state in the experience buffer where actually our robot had the object in its hand, on the table, but it had it in its hand because actually reinforcement learning was not able to figure it out or something like this, okay? But that's okay. It still shows that hint-centered experience bay helps over not doing that. And the same goal relabeling, which I just showed, can be used essentially in imitation learning. That's all I wanted to show you guys. The same ways, instead of having state action, you have state action, and goal, okay, in your expert trajectories, and you train your policy to condition also on that goals. And we'll see that goal condition imitation learning paper. But before that, we want to discuss about generative adversarial imitation learning, because this is going to be used on that paper. So do you have any questions so far? We have 10 more minutes and we have plenty of time to actually jump to our next topic. Yes.
Let's say in the extreme case, every goal was just the same as its state,
Very nice. Yes, exactly. So the goal state is chosen to be identical to the state space. And they tell you every state you can be in is a useful goal to achieve, right? Exactly. So your gripper could be anywhere in the workspace, and the same, your state space precise your goal state. Exactly, your goal state space.
So that's essentially like almost like a shortest paths optimization to like determine an optimal trajectory to get any.
Okay, very good, very good. So what you're saying now is that why don't I just do shortest path to figure out how to reach, as opposed to reinforcement learning? Reinforcement learning doesn't do that. Reinforcement learning is like, oh, let me run my policy. Oh, I got a random trajectory. Let me see if I succeeded and so on. What you are saying is use a planner. The reason that the whole point of using reinforcement learning is that in your environment, you may have actually obstacles like these guys here, okay, and say, okay, that you may not have actually exact perception of where they are, okay? And you can learn by trial and error to actually achieve different locations without planning. So we didn't talk about planners. Do you see? So this is just done trial and error learning. Is that clear?
But more robust because you don't necessarily.
With more augmented. So more augmented you with goals. That's all. So if you failed to reach here, but you reach somewhere else, then you use this as useful tuple to reach there. So now you train a policy across multiple goals, and you have more non-zero reward training tuples. Is that clear? This has nothing to do with shortest path planners, right? Okay.
Yeah, I was thinking in the extreme case if every state was a goal, potentially, and you knew all the states.
But you don't know. That's the thing. You don't know the dynamics of the environment. And I think what you're trying to say is this is really nuts assumption, not to know the dynamics of the world and assume you know the goal space exactly in the state space. I agree. It's super contrived. That's how many reinforcement learning papers work still. Do you see? I agree that I don't think it makes sense. But we will see other great things. This is still basics. That's we're done with the basics. From now on, anything we'll see on reinforcement learning will actually be extremely interesting. Okay. Okay. So here is we have 8 minutes, and there's going to be lots of fun. Now let me show you. So we just discussed about behavior cloning for imitation learning, and essentially what we described was a maximum likelihood. It's just a standard reinforcement learning problem. So basically maximum likelihood plus augmentations. That's all we said. Okay. We said it's a standard supervised learning problem. We're going to treat it the same as all other problems. So this is just maximizing the likelihood of expert actions, which in the case of continuous action boils down to least squares regression. Okay. And this is precisely what other reinforcement, supervised learning problems do. And the only thing that we're going to do to handle the distribution shift was data augmentations. So now I'm going to show you another way to handle that distribution shift, okay? More principled, difficult to get to work in practice, but extremely beautiful theory, all right? Okay? Very, very, very hot and very, very nice. So maximum likelihood. We have data and we want to maximize the likelihood of the data, all right? So we put down a probability distribution parameterized with some set of parameters, and we try to estimate those parameters so that under this probability distribution, the data is maximized. That's all. And we also have some conditioning information in our case, which is the state. So the data is essentially the actions. That's all. Okay. So our goal is essentially to minimize the KL between, R, the probability distribution we just parameterized, and the true data distribution. So P data, P model. All right. And you know what? If your P model is exactly the multivariate Gaussian distribution, as I show here, this exactly boils down to least squares. Okay. So that was our solution. Behavior cloning with conditions action, that's all it is. Now, the problem is the following, that there is distribution shifts, and this distribution shift came from the fact that we took whole trajectories, state action, and chopped them into individual time steps. And essentially, we neglected the temporal structure. We just treated them as individual data points. That's the problem. All right. And we said, make the expert actions more likely in the stage of the expert trajectories. Yes. But what about the states not on the expert trajectories? Well, we do not know. The actions are on constraints. That's specifically the distribution mismatch problem. Okay, I'm just repeating what we just said yesterday, earlier. So before we did data augmentation to handle this problem, now we're going to give a new solution that has to do with generative adversarial networks. We're just going to be building better distribution matching techniques between expert trajectories and the trajectories from our agent. Instead of neglecting the temporal structure, we're actually going to take this into account in some form. All right? Yeah, so our goal is essentially, we're going to define our distribution. We have a policy. Our policy defines a distribution over trajectories. And the goal will be the trajectories from my policy needs to match the distributions of the expert trajectories. Do you agree? This is the problem we're trying to solve. Okay. And before that, what we did is we chopped it into individual data points. We neglected the temporal structure, and we had to do hacks with data augmentations to handle the distribution mismatch. So now we'll do this in a better way. So just to give you a heads up, maybe, what we'll do is the following. We'll use GANs, general adversarial networks, to compare the distributions. Okay? Which distributions? The distributions for our generator, which the generator will be our policy, and the expert distribution. And how we compare them? Well, instead of maximizing likelihood, we're going to have this discriminator network that will be jointly trained with our policy. And that discriminator will look at tuples from the trajectories that you're going to be deploying from your policy and pairs, state actions, chops of trajectories from the expert. And basically, they need to be indistinguishable. Okay, that's the goal. So now, if your policy, you deploy your policy and you go towards the shoulder of the road, and most of your trajectories are actually your car crashing towards the road, then the discriminator will be able to tell the difference and say, I don't think the distributions here of states match. Okay, the states that I sample from your deployed policy and the states from the expert are actually not looking the same. And it will push us gradient to improve our policy to make those distributions more similar. Do you see what I mean? So we'll exactly be minimizing that state distribution problem that we have. Is that clear? A little bit or? Okay. So there are some, GANs were developed for generating images. So we'll start from there. And then we'll see how we'll adapt for generating actions. And there's a huge difference here that we really need to pay attention, that on images, everything is differentiable, while when we go to apply adversarial learning for imitation learning, there's going to be a non-differentiable part, okay? Basically, our policy needs to be deployed in the environment to generate trajectories. So that part is not differentiable. So we'll use policy gradients. Do you see? So that's good. So let's just wait to see. We have still 2 minutes, so we can still make some progress. Here is how GANs work. There are 2 networks. One is the generator. The generator takes a noise vector, for example, 50 elements. Each element is sampled from 0, mid, univariate Gaussian. And then you feed it into a network, and this spits out an image. Now you're going to say how a 50-element vector spits out an image where there's a fully connected layer, and then there is a tiling, and then there are convolutions. That's how the standard architectures are. And, there's been tremendous progress on what that architecture should be that goes from latent vectors to actual images. For example, the latest advances is don't sample just one vector, because if you want to really generalize, you need to sample multiple of them and have, attentions that communicate between them to eventually generate the pixels. So you can actually read, if you're interested, you can read this type of papers. So in any case, this is irrelevant for us. For us, the generator takes noise and goes through some differentiable function G and spits out an image, all right? And the sampling happens at the input. Once you sample the input noise, then the rest is the deterministic function. Okay, there is no stochasticity in the network. Okay, this is G. And here is D. D, the discriminator, is just a classifier. Just a classifier. It takes images and spits out yes and no. All right? It's just an image classifier. And it's trained as, again, a differentiable function. And for real images, the discriminator is trying to say 1. And for fake images generated by the generator, is trying to say 0. No, all right? So it's trying to predict if an image is real or not. So we just trained it as a standard image classifier. And we'll continue on Wednesday because it's 1:10. But the important thing to remember is that discriminator is just an image classifier. We don't train it till the end. These are just jointly trained. The goal of the discriminator is to tell to the generator, oh, all your images look pretty bad, but these look slightly better. Okay? It's just trying to use a learning signal to say, so the generator say, okay, I'll generate more of those. Do you see? This is precisely what we're looking for. We're not looking for training a perfect image classifier. Of course, it's extremely easy to train a discriminator that will say 1 for all the real images and 0 for all the generated images, especially in the beginning where the weights of the generator will be random. All is going to look like random noise. The whole point is that you train it a little bit so that you actually can confuse and give it a useful learning signal to kick off the learning of the generator, basically. Okay, that's all. So I'll see you on Wednesday. We'll talk about Guile, we'll complete Guile, and we'll also talk about imitation learning for manipulation.